Okay, so up to here is discussed in chapter 22 of the textbook, and from now on we will study chapter 23. So the lecture is going on a little bit longer, as I have said before, so please be patient. Okay, in chapter 23 we will study the Gauss law, and in order to study Gauss law we first have to describe the electric field flux. So therefore here let me explain to you what flux is. Probably many of you are not familiar with the word flux. The word flux basically means something flowing or amount of flow. Okay, just like the water coming out from this pipe. And actually the flow itself may be a vector. You know, the vector needs size and direction. So when something's flowing, the size may be the amount of flow, and the direction may be the direction of flow. But in fact, when we say flux, it is in fact integral or integration of certain vector quantity over a finite surface. Let's take a look at the figure on the right side here. There's something flowing to the right, and let's call it's the velocity. Velocity may be the easiest example of something moving or flowing. Okay. And then we are expressing this surface or area using a vector. Are you familiar with the area being a vector? Well, you know, again, area has a side, and then depending on how it's located, we can define a direction, which the best direction to describe this surface is the perpendicular direction. So therefore it has both direction and size. So area can be described as a vector. Okay, so in this case, the area vector will be pointing along the direction to the right. Okay, and in this case, you know, this area itself is located perpendicular to the velocity vector. So as a result, the area vector A vector will be parallel to the V vector. In this case, there will be maximum flow going through this surface, okay? And then think about the case where the surface is tilted by an angle theta, and then you see that in this case, again, the area vector is tilted away from this V vector, and then you can see that the actual amount of flow going through the same area may be smaller. And then if it becomes, say, angle becomes 90 degrees, just like this, then actually there will be no actual flow going through the surface, right? So therefore, in order to describe the amount of flow going through the surface, the best way is using a dot product. Okay, so this is how we define the flux. Okay, this is definition of the flux. And remember, as a big result, the flux is a scalar, and then basically what it means is a total vector flow through the area. And then let's think about a case when we actually put the area vector along this direction. Okay, in that case, now angle theta will become larger than 90 degrees, and then according to this definition, the flux may become negative. So flux can become negative, but what it actually means, basically what it means is that if the positive flux means the this flow going out of this surface, then a negative flux will mean flux coming in. So therefore, exactly opposite direction of flow. So remember the definition of the electric flux. Remember the definition of the flux, and it can become positive or negative, and it sometimes becomes zero. Okay, and in fact, what we want to describe in this chapter is not the flux of the velocity, but the flux of electric field. So therefore, following the same convention, we will define the electric field flux as a dot product between the electric field and the area vector. Okay. Isn't that simple? Okay, remember this is a definition of the electric field flux. And as a short comment, if there is any smart students, some fluxes are defined as a vector. And this note explains in certain cases that flux may mean vector, but I'm telling you, this is just for the students who already may know this, but most of you, it doesn't really matter. So, well, if you're not interested, let's forget it, okay? And as another preparation for studying Gauss law, let's try to see what a Gaussian surface is. Okay, basically the Gaussian surface is any closed surface with an arbitrary shape inside an electric field. And maybe the best example to think about is a balloon. Well, if you have a balloon, you cannot have a partial balloon or you cannot have a half balloon. The balloon has to be a completely perfect closed surface, which is completely surrounding the air inside. So that's a good example. And eventually what you want to do is you want to do an integration of the electric field around the entire surface. So in order to do that, you have to first divide the entire surface into many small pieces, and let's call this each piece delta AI vector, okay? And here on the figure on the right side, the examples are shown. So it's already cut into many pieces, and one example of example number 1, the delta A1 vector may be pointing along this direction, which is already shown here. And for the second example, it may be pointing along that direction. And for the third example, it will be pointing this direction. So area vectors are pointing different directions depending on the location. Sorry. And eventually, we want to make a dot product with the electric field, as we have learned in the previous slide. At each point position, the electric field may be different, so let's call them EI vector. So if you make a dot product between EI vector and delta AI vector, that will be the electric flux at that particular location. And finally, over the entire Gaussian surface, we will do mathematical summation, okay? But in fact, when we actually calculate this, making a summation over the entire area is of course not very simple, but there is a better way to do it, which is an integration. So here again, you are integrating the electric field vector with the area vector. In fact, you have to make a dot product and then integrate over the entire surface. And then again, this integration symbol with the circle on top means the integral performed over the entire closed surface. And in doing so, keep in mind that sometimes the flux through certain area may be positive, and sometimes maybe negative, sometimes maybe zero. And then here you get the idea that the electric field is actually going into the surface in this area, but coming out of the surface in the area. So depending on whether it's coming in or coming out, the electric flux may be negative or positive, okay? And as a final remark, some smart students may be asking that, why do we have to choose the area vector like this way? Instead of choosing the area vector going this way, why don't we choose the vector to be pointing exactly the opposite direction? Well, the answer is that it is okay to do so, but one thing you do not want to do is changing between these two possible choices throughout the semester. That will be very confusing. So in order to avoid confusion, let's make a promise. In this course, whenever you have a Gaussian surface, we will always choose the area vector to be coming out of the surface, not going inside, okay? Okay, and finally, we are learning Gauss law. So what Gauss law says is that a total electric flux through a Gaussian surface is proportional to the amount of charge enclosed inside the surface. It will be a good idea to remember what this says, but at the same time, we have to use mathematical expression, okay? So which is given here. Here, the first term, the first expression is, of course, the electric flux, electric field flux. And then what we mean by this is the total integration of the electric field around the Gaussian surface. And Gauss' law says that this value is proportional to the charges enclosed inside. And whenever you have two values proportional to each other, you need a proportionality constant. And then here, the epsilon naught, or actually the inverse of the epsilon naught, plays a role of the proportionality constant. And what is this epsilon naught? Do you remember its name? Its name is the electric permittivity constant. Okay. And then let's try to use Gauss' law to real examples, and then try to actually see how we use it. Okay. So on the figure on the right side, there are two charges, plus Q and minus Q. And then let's think about one Gaussian surface around this positive charge, which is S1. Okay. And then I'm drawing the shape very funny way to suggest that the shape doesn't have to be a sphere. You can take any shape. And then you can see that the electric fields are coming out of this surface. So therefore, according to the Gauss law, now total integration of the electric flux, electric field, is proportional to what? The amount of charge inside, which is plus Q. So we can write the Gauss law this way. And here, we have written it a little bit differently, and taking this epsilon naught to the left-hand side, and then, well, the shape looks a little bit simpler, but it's basically the same thing. So you can say that the epsilon naught multiplied by the electric field flux over the entire Gaussian surface is actually equal to the total charge inside, which is plus Q in this case. Okay. And then another example, S2, now surrounding the minus charge. Okay. And then here you can see that electric fields are going into the surface, but we have made a promise that we will always take the area vector going out. So you can see that here the electric field vector and then the area vector are almost pointing opposite direction. So therefore their dot product will become negative. So and then that is the case over the entire surface. So therefore, if you make the total integration, the value will become negative. And also, according to the Gauss law, it has to be minus Q. Okay, it's consistent. Okay, and then think about the another example S3, which is over here. And then you can see there's nothing inside, but because of the positive and negative charges outside, electric field is going in here and is going out here. But again, area vectors are always pointing outside. So in this area, their dot product will become negative. And in that area, their dot product will become positive. And then if you make a summation or integration, they will cancel. And then according to the Gauss law, it becomes 0. Why 0? Because there's nothing inside, right? Okay. So these two facts, how much is inside, must be directly related to what you get when you make a total integration outside, and that is what Gauss law is. Okay, and then let's try another final example, S4. Now this time surrounding both positive and negative charges. So in this case, you may be a little bit confusing to some of you, because now we have some charges, but electric field is at some place is going out and is going in. And then in this case, let's use the Gauss law, and what it says is that in fact each charge does not matter. What matters is a total enclosed charge. So therefore plus Q minus Q, you get 0. So therefore in this case, again, Gauss law says that if you make a total integration of the electric flux throughout this Gaussian surface, and what you get is 0. Okay. And then let's try to use this Gauss law to the previous case that we have learned. Before learning Gauss law, we learned how we get the electric field around one pointed charge based on the idea of the Coulomb's law. Okay, now try to use Gauss law in this case and see what you get. Okay, well, in the figure on the right hand side, there is one positive charge. And then how should we have the Gaussian surface? That's the first thing we have to do. And then, of course, the simplest way to put the Gaussian surface is making a circle. I'm sorry, not the circle, but three-dimensional sphere around it. And then, if you put the charges exactly at the center of the sphere, things will become very simple. And then, remember, well, if you consider symmetry, then you can easily guess that over the entire surface of this perfect sphere, you will always have the electric field pointing exactly away, and then the strength of the electric field will be all the same. There's no reason why it should be different from one place to the other. Okay, and then now let's try to use the Gauss law. Okay, I've already read this part. Okay, let's move on to the third next. And then here, even before doing the calculation or integration, you know that the outcome must be plus q, because plus q is the only thing inside. Okay, so we begin by having plus q. Okay, and then think about how we will do the integration of the electric field like this here. Okay, there's another typo. Okay, I will drop this. Okay. And then, again, remember what I said. So on any part of the area, the electric field will be exactly going out, which means that its electric field will be parallel to the area vector. So we don't even have to use the vector form, or dot product will always become 1. So we can rewrite that now. It is simply scalar product between E and dA. And then realize that it's a perfect sphere with the point charge at the center. Then strength of the electric field will be same everywhere. And then E now becomes a constant, so it can come outside of the integration. So finally, what you are integrating is the area vector over the entire surface. And then what value do you think you will get? And then what you will get is the total surface area of the sphere of the radius r. And remember what it is? It is simply 4 pi r square. Okay, so then now it's done. Okay, now you have equated the q with epsilon naught e multiplied by 4 pi e r square. And what you originally wanted to have was in fact electric field. By simply summarizing it, you get the answer. Okay, how does it look compared to the electric field you have learned in the beginning of this chapter? Okay, exactly the same. And then now you see why you had this funny constant, proportionality constant, instead of simple Coulomb's constant. This was exactly the reason why we had this expression.